In this video, we're going to look at another question, which was on a worksheet for work, energy, and power that I gave to my kids. And again, it's a past paper, and I can't remember where it's from. Shh. Anyway, so a 70 kilogram block is initially at rest. Whoopsie, didn't mean to do that. At rest, so initial velocity is 0 at the bottom of a rough friction plane inclined at an angle of 30 degrees. Great. The box is pulled up the plane by means of a light inextensible rope. In other words, the rope plays no role to play in the acceleration. It doesn't matter about its mass. Held parallel to the plane as shown, and the force applied to the rope is 700 newtons. Great. Now they say, what is the name given to the force in the rope? Now it's in a rope, so technically it needs to be called the tension force. Okay. Because there's no second object to this is why we're going to call it the tension force. Usually, if we were doing the free body diagram, we would now just call it a pulling force, okay, if there was a second object. Give a reason why mechanical energy of the system will not be conserved. Please be careful. You can't just say because there's friction, and it is because of friction. Friction, which is a non-conservative force, is present. Okay, friction, which is a non-conservative force, is present. Very, very important here. Okay, friction, which is a non-conservative force, is present. The box is pulled over a distance of 4 meters along the plane. So now I'm telling you that this distance, delta x, equals 4 meters. The kinetic frictional force between the box and the plane is 178,22. Not a nice value, but it's okay, we'll take it. 1, what did they say? 178,22 newtons. Brilliant. Draw a labeled free body diagram for the box as it moves up the plane. Again, so did not leave myself enough space for this, so I'm going to do it on the side. But it's at an angle, and I see this often. Somehow this box, which is on a slope, ends up going horizontally. Please don't do this. This is why I like to do what I'm going to do now. I know FG is going to go down. That's my tension. The normal force is at an angle to the slope, and then we've got friction, and that's very rough. So free body diagram means it's got to be a dot. So we have our dot. We have FG, and this is very thick. Let's make this a little thinner. There we go. We have kinetic friction. I really need to use the K now because they told you it was kinetic friction. Then we have FT, that was the tension force. We said it, we've named it as tension. And then, of course, we've got FN. So, we've got FT, which is the tension force. We've got Fn, which is the normal. Fk, which is kinetic friction. And of course the usual Fg, which is gravity. Worth 4 marks, 4 forces. Don't put the components onto this diagram as well. Make a choice. Either you put Fg or you put the components of Fg. You don't do both. I will suggest, this is my personal preference, that you only put Fg because you're less likely to miss out one of the components or put any extra forces on that shouldn't be there. Okay. Calculate the work done by the frictional force over the 4 meters. Well, that's fairly straightforward. We like a question like this because we remember work done by friction is going to be the kinetic friction, delta x, cos theta. I don't need to worry about any of the angles or the slope. That's irrelevant. They told me this was 178,22. X is 4. It's friction. So theta is 180. And we get minus 712,88 joules. Okay? Straightforward. Not really too difficult. It's the 180. Now they say use energy principles to calculate the speed of the box after it has moved 4 meters. There are several options for calculating this. Okay? There really are. And here it's about doing the simplest. And right about now, some of you are going, oh wait, we've worked out work done by friction, and we know, and I just want to show you why I don't do this option. Okay? It's work done, so we're looking at 9.5. Work done by the non-conservative force, which is what friction is going to be changing EK plus changing EP. Changing EK is definitely what we're looking for. Changing EP is where this gets difficult for us, because I don't know that height. I can work it out, no problem. Okay, it's up to you. I would prefer, and this is again a preference, so this I don't think is a great option. You're welcome to go do it on your own after I've given you this answer, and then see if you get the same answer. Then you really do understand this work. Work done, net work, is the change in EK. Net work means we have to use F net delta X cos theta. So this would be the EK in, I'm going to actually do it straight away with the numbers, with the letters. There we go. So this would be a half mvf squared, final velocity, that's what I'm looking for, minus a half mv I squared. Now it's about F net. Okay? You can find F net in the equation, alright, straight away. In fact, with this non-conservative force I was lying to you, this is actually Ft and friction. It's definitely more difficult. Okay, it's definitely more difficult. It's not just friction. So, F net would be my tension force minus Fg parallel, because that's going to act down the slope, minus kinetic friction. So remember, we've got my object. Here's my slope. There's Fg. So if I do my triangle, Fg parallel is opposite my angle, so this becomes Ft minus Fg sine theta minus Fk. Ft, they told us, was 700. My box was 70. This is 9,8. It's sine 30. And friction is 178,22. So we get 178,78. It's a coincidence that it's so close to friction. Please don't read anything into that at all. So, I know what F net is. 178,78. Delta x is 4. It's accelerating, so cos theta is 0. I have a half times 70 times Vf squared minus 0. Now it's a math issue. When you get Vf squared on its own, make sure it's a positive number. If you get a negative number, you've made a mistake, because you cannot get the square root of a negative number. Then you must remember to square root it at the end. And when we get there, we get an answer of 4,52 meters per second. Okay, not that bad. Then they say when the box is 4 meters up the incline, the rope accidentally breaks, causing the box to slide down to the bottom of the incline of the plane. What will be the total work done by friction when the box moves up and when the box moves down. Now I'm going to be careful here. Okay? We worked out that the work done by friction when it moved up was minus, what was it? Minus 712.88 joules. Friction can never do positive work. Okay? So if it did minus 712.88 joules on the way up, if it travels exactly the same distance on the way down, it's going to do the same amount of work on the way down. Therefore, the total work done by friction is 2 times the minus 712.88. It's going to do the same amount of work, same distance, same friction. Okay? And it has to be negative because friction cannot do positive work at all. Friction always opposes motion. I really hope that helps.